Okay, so in this video, I want to go over and begin to look at this idea of gas exchange and this idea that, everything we've talked about so far has been about breathing, the mechanics of breathing, the movement of airflow through the larger airways to smaller airways and alveoli, how we test for pulmonary function using spirometry, lung volumes. We've hit more on kind of the mechanics, what's going on in the lungs. Now we're going to kind of make this transition to, okay, so what happens to that air, that gas, oxygen, CO2, when we leave the lungs? And, ultimately the goal is to get oxygen from the air we breathe in to tissues that need it for aerobic oxidative phosphorylation, form ATP. And so we're going to now get in the second half of this, of looking at what goes on in moving oxygen to tissues that need it. So although we're leaving the lungs, we're not necessarily leaving pulmonary function as a whole. Because even though we're now going to enter into blood, and it's more cardiovascular system, the pressures of oxygen and the movement of oxygen in the blood is very much related to what goes on in the lungs. So let's go kind of with one basic idea. Pressure, I think I've said this before, pressure drives everything. And here now when we talk about blood flow, we're talking about movement of gases in the blood and through into tissues. Pressure is going to drive everything. And the key concept to understand here is Dalton's law. This idea that gas, any gas, whatever air, whatever that is made up of gases, is made up of whatever. And so the air you breathe in right now, wherever you are, unless something odd about the environment, you have oxygen in the air, you have carbon dioxide in the air, and what makes up most of the air you breathe is nitrogen. And if we were to measure the pressures of those gases, they would all equal the overall pressure of the air. Right? Now we call that overall pressure atmospheric pressure. And so where we are right now, assuming you're viewing this from Florida, where we are, we're at sea level, literally just across the way there. And so the pressure here is roughly about 759 millimeters of mercury. And that pressure is made up of the pressure of oxygen, the pressure of CO2, the pressure of nitrogen. Now, all these pressures are decided by the percent of those gases in the air. Now, the good thing is that these stay fairly constant. Irregardless of whether you're in Florida, whether you are on top of Pikes Peak, whether you're in Tibet, Mount Everest, these percentages stay the same. And so pretty much anywhere you go, the percent of oxygen in the air is going to be 20.93%. Again, anywhere, doesn't matter time of day, hot, cold, none of that matters. That percent generally stays fairly constant. CO2 is generally 0.03, 0.04% of the air you're breathing in. And the rest, about 79%, is made up of nitrogen. And if you add those up, and yes, there are some other minor gases there we're excluding, you get 100%. So if we want to know the pressure of each of those gases, so not the percent they make up of the air, but the pressure they exert, because again, air does have pressure, we would take the percent of that gas in the air, so in this case, oxygen is 20.93%, or 0.2093, multiply that by the total atmospheric pressure, or barometric pressure, which where we are right now, we'll just call it 760 millimeters of mercury. And when we do that, we get 159 millimeters of mercury. So the pressure, the partial pressure of oxygen right now in the air we're breathing in is roughly 159 millimeters of mercury. We can do the same thing for CO2, and we get a fairly small number. And we can do the same thing with nitrogen, and we get about 600 millimeters of mercury. So each of those gases has a pressure, a partial pressure. And that's going to be really key because pressure drives everything. And the goal is to get oxygen from the air we breathe in through the large airways, small airways, into the alveoli, from the alveoli into the capillary beds in the blood, and the arterial circulation, and ultimately to tissues, cells that require it. And in order to do this, we need pressure to drive this. This pressure is going to drive, and this is a good picture here to explain this, the pressure of oxygen is going to go from a higher to a lower concentration. So air, oxygen, in this case gas, will go from a higher to a lower concentration. So if oxygen is a higher pressure inside the alveoli as opposed to in the blood, it'll move from the alveoli to the blood. If the pressure is the reverse, as it is with CO2, then it moves in an opposite direction. And so because the pressures are higher in the air, lower in the body, we're going to see oxygen, because of this movement of air by pressure, move into tissues. But this pressure is affected by some things. And one of the key things to grasp is that oxygen doesn't simply just float in the blood by itself. Oxygen, because of its nature, has to be bound to something in order to make it from the blood and alveoli, make it to the tissues, whatever cells that require it. And so O2, oxygen, is bound to hemoglobin. Now, if you had me for nutrition, we know what hemoglobin is. Hemoglobin has a heme, has iron, has protein to it, and this is going to carry, it's going to bind to oxygen to allow it to make its way through the blood to its ultimate destination. And this is bound, wait for it, by pressure. And that's really key to grasp. We're going to talk about oxygen dissociation in the next video, and understanding that pressure keeps oxygen and hemoglobin bound together. If there's not adequate pressure to keep these bound together, they unbind, or the word we use is disassociate. So you need to have an ample amount of pressure of oxygen to keep oxygen and hemoglobin bound. You also, obviously, need hemoglobin. If you're missing any one of these, oxygen will not be bound to hemoglobin, and oxygen will not make it to tissues. And that's really key to grasp here, because there's more to getting oxygen to tissues than just breathing. You need hemoglobin. You need iron that makes up the heme of hemoglobin. You need protein, right? You need blood flow, obviously. You need a high pressure of oxygen. And if we're missing any one of these, that will impair the ability of oxygen to make it from the air you're breathing in, through your lungs, and to tissues that ultimately need it. And so that's really key. And this is why measuring hemoglobin and how much hemoglobin you have per liter of blood is incredibly, incredibly important. And so basically for most of you, we can carry about 150, 200 milliliters of oxygen per liter of blood, because assuming hemoglobin is fully saturated. In other words, we're assuming every oxygen molecule is bound to hemoglobin. Spoiler alert, that's not really the case. It's never 100%. It's close. It's usually 98% or so. And so we often say that oxygen has a certain percent bound, or certain percent saturated with hemoglobin. And we actually have devices that measure this. We have pulse oximeters. If you work in our cancer fatigue program, we use these all the time. And what a pulse oximeter does, quite literally, it's a little device we put on your finger, uses infrared to be able to measure the percent of oxygen that's bound to hemoglobin. And as you discover, it's never 100%, not surprisingly. It's usually about 98, sometimes 99, sometimes 97%, which is great. That's almost 100%. But there's always going to be a little bit of oxygen that doesn't end up being bound to hemoglobin. And this is going to be key, because there will be situations that we'll talk about in the next video where oxygen and hemoglobin don't stay bound and they disassociate, or what we sometimes say is hemoglobin desaturates. It loses oxygen, and when that happens, that oxygen will not make it to the tissues that need it. And as you can imagine, that's probably not a good thing, and it's definitely not a good thing. We'll cover that in the next